stretching, yes? What's that going to do to your dimensional accuracy?
Yeah, this spooling will actually be pulling. It will
That's
pull
going to
on
make
the
it
filament.
worse.
And we're going to have a sensor between that will sense the diameter. So
Okay.
if the diameter is too thin, it will add more.
What kind of resolution are, what
Bigger tip. If, say there's pulling, it's pulling into a smaller diameter, you would wrap it up with a bigger tip.
then what's going to happen? You're going to be spooling plastic that still passes class transition points, right? When does this solidify? Because when it goes below its glass transition points, which for PLA is 80 degrees Celsius, that's when it's dimensionally stable. Okay, when is that going to occur? And what kind of dimensional accuracy do you anticipate? How does it compare to off-the-shelf filament?
Preferably, we would have the cooling system directly under the sensor, so as soon as it comes out of the sensor, it is cooled down to the proper temperature.
It's going to cool down instantly?
Not instantly, but we would like it to cool down as quick as possible.
Okay.
And we haven't looked into the accuracy of our machine yet. We're still focusing on getting it to function properly, to at least produce this film.
Yeah, my other question there is you just kind of refer to safety as this nebulous concept. Can you expand on that? How can I injure myself with this? And how are you going to stop me from doing that?
Obviously, the housing is going to be no least to 350 degrees Fahrenheit buffer after you heat up the fan loop. So you can't just touch that, you burn yourself. So obviously you're going to have to protect that with some type of heat tape, insulation, so it doesn't harm someone. They would put their hand in there and grab the housing and they would burn themselves.
Yeah, something to consider there is every warning label you see is there because someone did something stupid, and your regulations are written in blood. Okay? This is a big shredder that you're describing. It takes about as much force to bite through a finger as a baby carrot. What happens if I get my hand caught in that? Is there an e-stop? Interlocks?
The shredder is not actually going to be implemented in the machine. The shredder is going to be outside. It's going to be outside the machine. Right now, this machine is only putting pellets in and shredded material already down.
Okay.
The shredder is an additional
Accessory.
So the shredder is your stretch.
Yes.
Yeah, it's going to be an additional accessory. Right now, it's only a funnel. You put your hand there. It'll probably be hot, so you put your hand there if it's on. But there's no shredding in there.
Okay. Thank you guys. Okay, next up we have Overcast weight watching system. I like this one. Yeah.
Good morning, everyone. My name is Lucas Miller. I'm Andrew Waffle, and today we're going to be talking to you about the Overcast bait launching system. So, in this talk, we're going to hear about the background and why we chose to conduct this project. We're going to hear the requirements and what it has to do. We're going to go through our scheduling phase, our budgeting, our design. We're going to talk about some ethical considerations and what we accomplished this semester and what we plan to accomplish next semester.
All right, so the problem we're trying to solve is related to surf fishing or fishing at the beach, more specifically the limitations of hand casting. Most beaches have turbulent water or wave formations that form anywhere from 100 to 200 yards offshore, and the goal of the fisherman is to cast beyond these waves. However, even with an experienced fisherman, it's quite difficult to achieve a distance of above 100 yards, and this video represents that problem. In order to solve this problem, we're going to be designing a pneumatic bait launching system capable of launching a projectile up to 300 yards into the ocean. This system will feature an accurate and controllable launch distance with numerous safety features.
So here we have a breakdown of some of our requirements for this project. It's broken into 5 main categories. The first is computer control. That's going to give us our accurate launch distance. Second is easy portability. It's going to be easily maneuverable along the beach. Third is our 300-yard maximum distance. Fourth, and most importantly, is our safe operation. We want to ensure that anyone using the system and anyone around it while it's in use is safe. And fifth is our deliverables. That includes our technical documentation or managerial paperwork. So next up, we'll get into some mechanical design parameters of this system. First off, we have a 2-inch inner diameter barrel that's 4 feet long. We have a 280 cubic inch pressure cylinder that's going to hold our pressurized gas. Third, we have extendable legs. These make a wide angle. They're about 4 feet long. This gives us a nice firm mount on the beach. Those legs can fold in. When they're folding in, the wheels at the end of them protrude slightly, and that gives you an easily wheelable assembly that's going to make it easy to pull it along the beach, similar to the fashion of a golf caddy. Next, we have waterproof enclosures for both our battery and our electronics. Make sure they don't short or anything like that. And last but not least, we have solenoid valves for both pressurizing the cylinder and firing the projectile. Some basic structural materials that we used for this project were aluminum for the structural components, like the barrel, the frame, and the legs, as well as the pressure cylinder. Next, we had plastic for the battery box and some of the mounting brackets, rubber for all of our gaskets. We use brass for our pneumatic fittings, that includes crosses and T's, and we use stainless steel for the transfer pipes between those fittings.
So the projectile is designed as a package consisting of the hook, bait, and weight, all frozen in ice with the line coming out the back. The model is going to be molded as shown on the screen, and it's going to have dimensions of 7.5 inches long by 2 inches in diameter. And this projectile will weigh anywhere from 0.95 pounds to 1.3 pounds, depending on the user hardware.
So at the heart of this project is the computer control system, that being a Raspberry Pi 3 Model B+. The user is going to have to input 2 values to the system. One is the weight of the projectile they're launching, and the other is the desired launch distance. The Pi is going to use these parameters to calculate the required pressure to achieve that distance. Now, 2 things need to be kept in mind. It needs to know the angle of the barrel relative to the water, and it needs to know the pressure in the cylinder at all times. It needs to know the angle of the barrel, because most beaches tend to slope downhill towards the water, so you need to compensate for that, and also know that you're at the ideal launch angle. You also need to know the pressure in the cylinder, so that way when you reach that from your pressurization source, you can cut it off to achieve that accurate launch distance. The user is going to interact with this control system from an LCD touchscreen. So to see this project through its lifespan, we broke it down into a couple basic components. First, we have our initiation phase, which is where we define the scope of the project and why we want to conduct it. We have our mechanical design phase, which is where we perform our physical calculations as well as design the apparatus itself. We have our electrical design phase, which includes the mobile power supply unit, as well as writing all of the software to control it. We have our prototyping phase, where we build it, test it extensively, and see if there are any deviations from our expected performance. We have our specification phase, which is where once we achieve the goal that we set out, we're going to write down all of the technical documentation regarding our final system, the one that we have in hand. And finally, we have our deliverables phase, which is where all of the paperwork is delivered to the user so that they can have a safe operation every time they use it.
Here's a condensed version of our schedule that we were following for this project. As you can see from the Gantt chart on the right, that it's split into 2 components, the first semester and second semester, with the first semester having 2 paralleling schedules, the mechanical section and the electrical section. As we move on to next semester, we're going to start working together more with the fabrication.
Here's a quick note on the components we use. This is our bill of materials. It was broken into an electrical and mechanical portion. You'll notice down at the bottom are projected and actual totals. The projected total is what we would expect to pay if we were buying everything new straight from market. The actual total reflects all the components that we already have in possession and thus have reduced our cost. We'd like to note that we are currently about $25 over budget, but in the coming days we will be working to reduce that figure. Here are 2 final renders of the system showcasing all of the operational components.
So this heat map represents the culmination of our calculations conducted this semester, and it shows the pressure required to achieve a launch distance of 300 yards with varying chamber volumes and projectile weights. You can see that the heat map is split into 3 sections, with the lines representing our desired upper and lower bounds of pressure, the upper bound being 150 psi and the lower bound being 100 psi. We determined our chamber volume to be 280 cubic inches based on materials that we found in the machine shop, and from there we compared compared it with the typical projectile weights of 0.95 pounds to 1.3 pounds. As you can see from the red box, our calculated pressures are well within our range of desired pressures.
Here's a graphic of the angle adjustment system. As Lucas mentioned earlier, we do have to account for the downslope of the beach. To do this, we've implemented a ratchet pawl system that has a 25-degree range of motion. That 25 degrees is split into half-degree increments using 50 teeth. It has a spring-loaded pawl so that as the user adjusts the angle, it sets it into place. The user can then clamp it and lock it in place. This prevents the barrel from moving during the firing process or from being influenced from any environmental factor.
So this render shows the 5 main inlet components of our pressure chamber. The first being the pressure transducer. It's going to read the pressure inside of the chamber and send a continuous signal to our computer system, which will be displayed on our screen. The inlet solenoid valve will control the airflow from a pressure source such as a air compressor and will close when the desired pressure is achieved. A 200 psi manual pressure gauge is also added as an extra safety feature in case the electronics components malfunction or fail in any way. And a 175 psi pressure release valve is also added for extra safety. Lastly, a manual Schrader valve is included that is compatible with a bike pump in case a user wants a different alternative of pressurization.
Here's a graphic kind of showcasing all the operational features. The first is a fishing rod holder. This is going to be made out of stiff plastic. This is necessary because a lot of surf fishing rods range anywhere from 10 to 12 feet long. Second is our waterproof battery box. This has a lid and a gasket around the edge so that the user can easily remove the battery, charge it, and replace it. Third is our splash-proof screen and electronics box. As Lucas mentioned, this is a touch screen that's going to make it easy for the user to interface with the control system. That whole electronics assembly is easily removable in the case that the user would like to perform a washdown of the entire system. Fourth is our solenoid release valve. That's mounted at the back of the assembly there between our pressure cylinder and the diffuser of